proposals are due today. Hopefully everyone's been there already. So the so a few of you have asked me if something comes up and you want to change or switch groups a little bit. It's probably okay. What's in the proposal is not binding. In fact, for some of you, I may give some recommendations to alter things a little bit, trying to guide you towards something that'll be a better project. If you if you want to change something, that's probably fine. Just check with me and let me know. So the next thing for the project is the data collection report, and that's due in a few weeks. I forget the exact date, but I'll try and get feedback on these. Hopefully within the next week or so, I should be able to get through it and give you some feedback. And the homeworks we'll probably get back at some point next week. So it'll take a while to get the grading all set. All right. So for the last three lectures, we kind of went through kind of a series of a series of 3 lectures that built on each other, where we started with taking some text documents, showing how to convert these text documents into sets so that you can compare the similarity between them. And then this was inefficient, so we showed how to use this min-hashing technique to get through the vectors. And then for vectors, we showed how to do locality-sensitive hashing and allow us to do things fairly efficient. And along the way, you saw that there's this trade-off between modeling, what modeling you do to it, and to get it into some form that you can deal with more generally, and some approximation you're adding into it to make it more efficient of how to do certain some similarity calculations. So in the in class today, I'm going to talk. I'm going to kind of break away from this sequence and kind of talk about more of a potpourri of stuff. So we'll talk in general about distances. So this seems very generic. The last couple lectures have been more about the efficiency of doing things. This will be more about the modeling. And so I'll start by defining some things precisely, and then I'm going to go through some examples of some distances in roughly this order. So I'll go through the L2 distances. This is familiar L2, L1, L0, L-infinity. Quickly mention the Jacquard distance. We'll talk about the cosine distance, which is kind of a useful alternative to these has different properties. And also similarly the KL divergence, which kind of has which has an information theoretic feel to it. The edit distance and the graph distance. And so this will kind of be the order I'm planning to go through. So many of you have probably seen at least some of these distances, maybe most or all of them. So even if you've seen them before, hopefully you'll kind of learn some new insights about these. I'll kind of define them and then kind of talk about the modeling aspects, how to think of how they're dealing with data. And the point of this is that there's not just one distance between two types of objects. There are many ways you can define a distance, and this is a choice. This is a modeling choice, and you probably shouldn't take it too seriously. Don't put all your faith saying, well, the L2 distance said these two were closer by a little bit. Well, that's because you chose L2 instead of L1. Why did you choose L2 instead of L1? Well, probably it was easier to work with, but maybe it didn't model things, as good as L1. So I'll kind of go through these and kind of give you a flavor of a lot of different classes of distances. So I'm starting by kind of doing this outline because, if you have particular interest in any of these, I can probably spend more time on them. Please let me know. Or if there's some other sort of object you're interested in about what's the right way what are common ways to define a distance between these sorts of objects, I'm happy to kind of entertain. So this will be kind of like, I'll kind of go through these, but it can be a fairly free-form lecture. You can stop me, ask me questions, and so forth. Okay, so before we go on, need to stop the blue, and so I'll start by redefining a metric. Is this green color okay? Often I can't see green in the back very well. Okay, let me try again. That's why I bring lots of markers. Okay, so a metric. So I defined this before, but let me just write this up again. So because we'll be referring back to this throughout the lecture. So we'll be talking about so a distance between two objects, A and B. And so the first property, M1, is that this is always greater or equal to 0. Right? So this is not negative. A distance can't be negative. It can't take you a negative amount of time to get from here to there. Right? So these so M2, A and the distance between A and B is equal to 0 if and only if A is equal to B. Right? So two things have only a distance 0 if they're exactly the same. The third one is about symmetry. So AB is equal to D of BA. The distance to get from A to B is the same as the distance to get from B to A. Clement.
So yeah, in this matrix, the second assumption, the distance between 2 points A and B equals 0, exactly if and only A is equal to B. So this is often not a, you don't often achieve this in real world scenarios because the A and B are usually some kind of models. And for example, if you convert text to the models that are used or most of the companies use today, you will see that you have actually at the beginning two different texts, but when you model them, they are the same quantity, the distances between them is 0. So the second
so the comment is that, so this is not always the case in all modeling and in all distances we use, and we'll see some examples where that's true. So I'll give some examples where this case where the distance is 0 if and only if they're exactly the same is not always the case. So I'll be talking about abstract inputs. So A and B will represent, say, sets if we took the k-grams of documents. Right? It could be we had two different documents that had that have the same k-grams. So the distance between the sets is 0, but the documents are not exactly the same. So that meant that in the modeling step, we lost something, and even though the distance we considered was a metric that satisfied this property, it did mean the documents were actually the same. And that's a problem where we lost this in the modeling step. Right? It's not a problem with the actual distance. Now, there are other things that are distances which won't satisfy all these properties, and they're perfectly good. And we'll actually see an example of a good distance that is very commonly used that does not satisfy this property. So good comments. So feel free to ask me about these things. So I'll try and cover the kind of important things to to pick out from this, but it's helpful to have interaction. So, and the third thing is the triangle inequality, which is the distance from A to C is always less than or equal to the distance from A to B plus the distance from B to A, right? So this can often be seen by a triangle if you have 2 points A and C, and there's another point B, then if you take the straight path from A to B, it's always, this says that it's always shorter or equal than if you went through this waypoint B. B to C, right? B to C, yes, thank you.
Yeah, that was my
No.
comment.
Okay, yeah. Oh, and so I want to say one more comment about M3 here, this thing about symmetry. So this is saying, like, if A is your house and B is school, and it takes you 10 minutes to get from your house to school, well, it may not be true that it takes you 10 minutes to get from school back to your house. This may be the case because when you're going to school, you get to take all these right turns, and on the way home, you have to take all these left turns, ignoring traffic issues. But because of this, it may take longer, and so this also is not always true in many real-world scenarios and in some businesses. So there's a lot of nice stuff that will happen if you have a metric. So we'll talk about some more techniques on Wednesday for detecting similarity between one object and a set of objects very quickly, and a lot of these techniques generalize to any distance which is a metric. You kind of need these different properties to get these techniques to work. Sometimes you can relax these properties and still kind of get it to work, but it's a lot more difficult, and often it doesn't work quite as efficiently. So having these kind of abstract properties is a very useful thing to keep in mind. And they kind of make sense in what you would generally want out of a distance. Okay. All right, so we'll start by talking about these LP distances. Okay, and these are defined on vectors. All right, so I'm going to have A and B are going to be in RD. So this is, this is a d-dimensional. This is a d-dimensional space, and so, for instance, I can write A as A1, A2, A3, AD, and remember when I write it in these parentheses, this means it's an ordered tuple. So A1, if I switch A1 and A2, it's not the same point anymore. So it's not a set. So it's an ordered set in particular of D objects. So then the LP distance, and so P here. So P here is a parameter. The LP distance is going to be now defined as the sum 1 to D of AI minus BI to the power P, and then I'm going to take all of this to the power of 1 over P.
This is not absolute value. Absolute value. AI minus B.
Yeah. Yeah, that's right. Yeah. And sometimes you write this as just A minus B P. So if this is the L2 distance, then this is the 2 norm. And so this notation is actually the norm notation of a single vector. So you can actually define a vector C, which is equal to, where say C1 is equal to A1 minus B1, C2 is equal to A2 minus B2, and so on. And then this notation C is just the P norm of this vector. So then that's essentially measuring the distance of the vector C from 0. Okay. So the most common, or one of the most common versions of the LP distance is the L2 distance, and this may look a bit more familiar. And so here I don't actually need the absolute value because the square always makes things positive. And then the 1 over p power is actually a square root. Taking something to the 1/2 is actually taking the square root. Okay, and so this is, if I draw these points, and I have A and I have B, then this distance actually represents the straight line distance in between the two points. Okay? A more interesting way of thinking about this is that if I'm thinking about this now as the distance between two things, but let's say I can think of it as the norm of some vector C. So I'm measuring the distance from 0. So let's put the origin here. Okay, and now I'm going to draw a unit ball under the L2 norm. And a unit ball is going to look kind of like what you expect. It's going to be a ball. So this should be a perfect circle. That's not perfect, but I guess I did okay. And so this is 1, 0, 0, 1, minus 1, 0, and 0, minus 1. All these points where it's crossing the axes here. So this is only, I can only really draw in 2 dimensions here, but you can imagine this would be the same in higher dimensions. It's going to be all the points at a distance of 1 from the origin. Remember, we're thinking about some point C here. This could be a point C. This point C is a distance of 1 from the origin. So if I have like 2 points A and B, and the vector between them is the same as this vector to C, they're going to have the same distance. This is 1 and this is. Okay, so this seems pretty obvious, but it'll be a little bit more interesting if we write down the other metrics, or the other LP distances as well. So this is going to be the L2 ball. The L1 distance, just write this down, is also pretty easy. It's just going to be, now this p power to the 1, it's not doing anything because it's a 1, and 1 over 1 is 1. So now we just have the sum of the differences between each of the coordinates. Okay, so what is, if I wanted to draw all the points which are distance 1 from the origin under the L1 distance, what is this going to look like? It's not going to be the same as the L2 ball. So is this point going to be a distance 1? This point 1, 0? Right? So this point is still a distance 1, right? It's same for all of the points on the axes here. In every case, I just have the sum over these 2 coordinates now, and always one of the distances is 0, the other one is 1. Because in this case, B, it's like saying B is going to be equal to the origin. Its coordinates are 0, 0. So if A has one of the coordinates 1 or -1, the other coordinate 0, then the sum of the absolute values is going to be 1. Right? So all of these points that where they intersect are all going to be a distance of 1. Right? But those are going to be the only places where it's the same. So how about a point, let's look at this point right here. Let's say if c was equal to 1 over square root 2, 1 over square root 2. Okay? So if I look at this distance from the origin under the L2 distance, I claim, so this is on the unit circle, so I claim this should be a distance of 1. So that means I'm going to get, so this sum over these two terms, 1 over square root 2 minus 0 squared plus 1 over square root 2 minus 0 absolute value squared square root. Right? So this was the L2 distance of this point, and this is going to be 1/2 plus 1/2 square root, and it's going to be the square root of 1 equals to 1. Right? So under the L2 distance, I get a distance of 1. All right, so under the L1 distance, right, this is a perfectly valid distance. Under the L1, I'm going to get 1/2 minus 0 plus 1 over square root 2 minus 0, this, right? So I'm going to get, and this is going to be equal to 2 times 1 over square root 2, and 2 over square root 2, which is going to be slightly more than 1. Right? What is this going to be? Something like 1.4? Right? So this is more than 1 now. So this point is now outside the unit ball under the L1 distance. Okay? So that means that the unit ball is going to be inside of here somehow. Okay? So how is, if I went in this direction until it was a distance 1, how far do I go? Right? They're both going to be, x, y coordinates will be the same if I'm along this direction. And they need to add up to a distance of 1, so they should both be 1/2. Right? So if I'm at 1/2, this point is at a distance of 1 from the origin, as well as this point and these points as well. Right? And I'm also going to get these points here that are going to be at values 1/2 with a negative sign. Okay, so how do I complete this?
It's a straight line equation.
Yeah, so it's not a square, it's going to be a diamond. Okay? It's going to be straight lines through here. So this is the L1 ball, L1 unit ball. Okay. So, what? Well, it's a rotated square. So if you tilt your head sideways, it's a square. So so actually on that thought, let's write down the L of the L infinity distance. Okay, so L infinity is kind of weird here. Now P needs to be infinity. This doesn't quite make sense. So we kind of define it. What would happen is if you took P to a really, really large number, to the limit, it'll be infinity. Then it's going to be, so we're going to, it looks like we want a b to the power infinity square root, or not, so to the power 1 over infinity. So this one is going to be equal to the max of I in d of AI minus EI. Okay. So I'll draw, well, so the reason to think about this is as you're increasing the exponent p, what's happening is that so what's happening is that certain of the points which have a further distance are becoming more and more important, right? They're becoming more relevant towards this sum, right? So if I have 6 numbers, 1, 3, 7, 100, 2, and 4, and 3, okay? And I took them all and I squared all of them. All of a sudden, 100 squared is 10,000. All the other ones are under 50, right? So the bigger the number is, the more important it is to a sum here. Okay, so what's happening is as p goes to infinity, only the biggest differences matter. And eventually, but then you're taking them by 1 over square root of infinity, so you're kind of canceling that out again. So it kind of, in the limit, it becomes the max of a minus b. Okay, so people write L infinity, and they really mean the max here. They mean, so this is what's meant by the L infinity distance here. Okay, so now what would the L infinity unit ball look like here? Okay, so I'll give you a hint. These 4 points are still going to be unit ball. Because, let's look at this, the maximum difference between any of the coordinates here. One of the coordinates is exactly the same, the other one is a distance of 1. Right? So this point is still in unit ball. Same with these 4 points here. Right? So how about this distance, this point C, which is on the L2 unit ball of coordinates 1 over square root 2, 1 over square root 2. What's the L infinity distance from point C there to the origin? So what's the maximum here? So B is going to be the origin, so it's 0, 0. And A is 1 over square root 2, 1 over square root 2. So what is the L infinity distance going to be? So that may have simplified to the right thing. So the L infinity of, let's write this down, 1 over square root 2, 1 over square root 2, 0, 0 is going to be equal to the max of these 2 quantities of 1 over square root 2 minus 0 and 1 over square root 2 minus 0. Okay, so both of these quantities is actually, these are equal to 1 over square root 2 and 1 over square root 2. So the maximum of these two is 1 over square root 2. So this is about 0.7 something, right? So this is less than 1. So this quantity is less than 1. So so maybe this is what you're trying to say, but but this point is inside, now is inside the unit ball. So this is less than a distance of 1. Okay, so if I were going in this direction, how far do I have to go until I hit a point at a distance 1 from the origin? Yeah, that's right. Yeah, so I can have, as long as both of the coordinates are less than 1, as long as they're both less or equal to 1, I'm within a distance of 1. Because I look at the maximum difference. Right, so this point is inside the unit ball. And in fact, the same is true for all of these points here. And so to complete the unit ball, as long as either coordinate is less or equal to a distance 1, it works. So that means this is completing the square here. So back with your comment of the L1 distance being the square, well, really the L infinity distance is the square, and L1 is kind of a rotation of the square. Okay? So this is important, that one is a rotation of the other. There are lots of techniques where you're trying to do something under the L1 distance, and you can use some advantages of it being this perfectly rotated square. It's orthogonal edges and so forth, and if you want to compute something under the L infinity distance, you can actually rotate all your coordinates by 45 degrees and use the same techniques. So it's important that one is a rotation of the other. They're computationally, in many ways you can use similar tricks to work with them. But it's also important to note that if you were to rotate your coordinate system, and actually we'll do some, when we talk about PCA as a form of regression in a few minutes, we'll actually talk about rotating the coordinate system. We want to do this to find the best kind of fit of coordinates through some data. It's important that only L2 has this property that is you change the coordinate system. And what I mean by that is instead of having, say, the x direction here and the y direction here, I can do something where the x direction goes this way, this is x prime, and the y direction goes like this. They're still orthogonal to each other. This is a different coordinate system. So now a point here at C, okay, one of these points C, I can write new coordinates in terms of x prime and y prime here, and we'll talk about this more. The L2 distance is exactly the same. I have not changed the L2 distance. It doesn't matter what the coordinate system is. And this is a very nice property about it. But the L1 or L infinity distance, it changes. The distance has now changed. So if your coordinate system is special, then you need to pay careful attention to which of these metrics you use. If your coordinate system is kind of picked somewhat arbitrarily, and the different coordinates may, could be swapped or rotated, then you should be using L2 probably, because that means you're not saying something special about the individual coordinates. The individual coordinates, the ways you've labeled them don't matter. And so if you choose L1 or L infinity, this modeling choice has somehow influenced your distance, where L2 was not influenced by that. Okay. So at the beginning of next lecture, I'll talk about an example of a high-dimensional data point that you get like this in 128 dimensional space. So there are these features that come out of image processing they're called SIP features. And so when you're trying to understand images, you try and find particular points in the image which are somehow special, and you give them as representative a 128 dimensional vector. So then D, this is a 128 dimensional space, and all these coordinates are, they mean something in particular, but they're not, it kind of matters to pick the L1 or L thing distance. The coordinates correspond with each other. And so it makes sense to think of one of these distances and where you would get this from. There are other situations where you may be rating some large number of movies with some numerical value. And you want to think of kind of a space of all movies, and these movies are just representatives of them. And then it may be better, it can make sense in some ways to kind of throw away the idea of individual movies. There's a space of movies, and this individual rotation of the coordinate system is not as necessary anymore. And so we'll kind of come back to these examples. But this picture is I think, an interesting way of thinking about these distances and the properties of them. As you get to higher dimensions, these these shapes kind of go with you and they become even more kind of, these shapes become even more distinct. Okay, so just as a thought experiment, what will this L infinity ball look like in 3D?
L infinity.
Yes, so it's going to be this cube, this 2 by 2 by 2 cube, right, centered at the origin. Right, so it's going to kind of come out from the board kind of as out like a flat piece coming out like this, right, to distance 1 and also go into the board. So how about the L1 distance here, the red one? What is that going to look like in 3D?
Again a cube.
Yeah, so think of the z coordinate here coming out, and a coordinate of 0, 0, 1, which is a 1 for the z coordinate and 0 for the other coordinates. This will be on the unit ball. But as I come back here, it's going to be a straight line here, right?
It's like two pyramids.
So yeah, you're going to kind of stack a pyramid out this way and also one going into the board. It's a rotated cube again, but it's smaller, right? It's inside of here. But you know, both the L infinity cube and the L1 rotated cube, or kind of diamond, they're both kind of pointy, right? The L2 ball. So this was the L2 ball look like in 3D? Right, it's going to be a sphere, right? And a sphere and everything inside of it is a ball, right? So, so this is very round, and it stays round in higher dimensions. Whereas the L1 and the L infinity, they keep getting pointier and pointier, right? And so let's, to kind of think about this, you know, try and imagine what these look like in higher dimensions for a second. It's kind of, you can kind of go to 3 dimensions, then in maybe, well, it's kind of similar in 4 and beyond. The L1 gets very pointy, and it's very easy to get to a higher distance if you travel along one of the coordinates. The L infinity, you know, in order to get to, so actually that was the wrong intuition, sorry. So at L1, the hardest way to get to a large distance is to travel along